Hello, Matthews Gatos here. Welcome to a special video about factoring special polynomials. We're going to look at three special types of polynomials and how we factor them. So the first special polynomial is a polynomial that has two variables. So not just an x, but maybe an x and a y, an a and a b. So if we can multiply binomials with two variables, x times x is x squared, x times 3y is 3xy, y times x is xy, y times 3y is 3y squared, grouping my like terms in the middle to get 4xy. That means we can factor polynomials with two variables, because if I multiply those, I end up with this polynomial. So that means that this polynomial factors as this. So let's look at an example of how we can factor a polynomial with two variables. So I want you to use the same process as before. Factor it as though there were only one variable, and then just add in your second variable in your factors. So for example, c squared plus 3cd minus 28d squared. So I'm just going to focus on my lonely number, even though there's a d squared, my last number. So I'm going to ignore d temporarily. So my lonely number, if I ignore d, would be negative 28. My middle number would be positive 3. So I'm looking for two numbers that multiply to negative 28, add to positive 3. So I know since it multiplies to a negative, one is positive, one is negative. And since it adds to a positive, I know that this is my bigger factor. So I just need to think about the factors of 28, like 1 and 28, 2 and 14, or 4 and 7. So the bigger number, 7, the smaller number, 4. Let's check if this works. 7 times negative 4 is negative 28, yes. 7 plus negative 4 is positive 3, yes. I am good to go and factor. So the only way I can get a c squared is c times c. The only way I'm going to get factors that multiply to negative 28 and add to 3 are the positive 7 and the negative 4. But now we can take into account our d squared. The only way I can get d squared is d times d. So let's check just to make sure that I did in fact factor that correctly. So just apply the distributive property by multiplying c by c, c by negative 4d, and then I'm going to distribute 7d in, so 7d times c, and 7d times negative 4d. Grouping my like terms in the middle, I have negative 4 cd's, and I add 7 cd's, which is 3 cd's. Take away 28d squared. So since I end up with what I started with, I know that my factors are correct. Okay, second special factoring that we're going to look at involves binomials being squared. Let's look at what happens. I want to square these binomials, and I want to look for pattern. Remember, when you square, it just means multiply it by itself. So x times x is x squared. X times 6x, 6x times x, and 6 times 6. I'm going to leave that unsimplified just for a minute, and I want to look at my next one. So 3x minus 7 squared means 3x minus 7 times 3x minus 7. So in my first one, I have 3x times 3x, which is 9x squared. 3x times negative 7. Negative 7 times 3x is going to be 21x. And then negative 7 times negative 7 is positive 49. So I'm looking for patterns. So the first thing I notice is that my first number is a perfect square and my last number is a perfect square. Same thing happens here. So perfect squares are numbers that have two identical factors. So x times x, 6 times 6. I also notice they're both positive, the first and the last term. Then in the middle, I see that there are two identical terms. 6x and 6x is 12x plus the 36. Over here, I can see I have two identical terms, which is negative 21 twice. So combining my like terms, I end up with this. Okay, so this pattern here of squaring a binomial creates a special type of a trinomial called a perfect square trinomial. So whenever we have something that is squared, we can use a pattern to actually go ahead and expand it. So my first pattern is going to be x squared, the first number squared, 3x squared. So 2x squared would be 4x squared. I have my other pattern where I have 6 times 6 is 36, negative 7 times negative 7 is 49. So in this one here, it would be positive 5 times positive 5. And then that middle term is double. So see how I have x times 6, doubled is 12x. Here I have 7 times negative 7, 3x times negative 7 is negative 21x, but it doubles to be negative 42. I'm going to do the same thing here. So these two numbers multiplied together, 2x multiplied by 5 is 10x, but I'm going to double because I know I have two middle terms. So that is the pattern that I can use to expand it. So again, this trinomial has a special name, and that is the perfect square trinomial. So anytime you take a binomial, square it, you're going to get a perfect square trinomial. So we can use this if we recognize perfect squares to factor, because then it's easy to go backwards. Here's how I recognize it. My first number is a perfect square. My last number is a perfect square. And if I take the square root of those two and double it, I get my middle term. So 2 times the square root of a squared times the square root of b squared. So that's 2ab. So doubled in the middle. And then adjust the sign. So if this is positive, this is positive. If it's negative, it stays negative. So let's use that pattern to factor this perfect square trinomial. Okay, so you can see I take my x squared, I take the square root of it. So I take the square root of x squared and I get x. The square root of 9 is 3. And then 3 times x is 6. 3x, sorry, x times 3 is 3x, doubled is 6x. So really what I do is I take my square root factors and I double them to get my middle term. So let's try and factor this one here. So it looks like it's a potential for a perfect square because 4g squared is the same as 2g squared, and 49 is the same as 7 squared. So the first and the last term are perfect squares. If it is a perfect square trinomial, I'll take this factor, 2g, I'll take this factor, 7, and I'm going to double it. If it works out to be 28, this is a perfect square trinomial. So 2 times 7 times 2 is 28g. So this, in fact, is a perfect square trinomial. So I just take the square root of the first term, which is just 2g, the square root of the last term, which is 7, and the sign of the variable term, which is positive. So that perfect square trinomial factors as 2g plus 7 all squared. So remember, perfect square trinomials factor as binomials squared. Okay, and this is our last type of perfect squares, or sorry, perfect or unique polynomials. These are the same but opposites. So see how the factors are same but opposite? X plus 3 and then x minus 3. 2z minus 7, 2z plus 7. I want to expand this and see if I can come up with any patterns. So x times x is x squared, x times negative 1, 1 times x, and 1 times negative 1. So notice in the middle here, these cancel. Negative x plus x, that cancels. That's just 0. And I'm left with just x squared minus 1. Let's try that in the next one. So 2z times 2z is 4z squared. 2z times 7 is 14z. Negative 7 times 2z is negative 14z. And negative 7 times negative 7 is 49. So again, I get rid of my middle term in the middle. 14z take away 14z is 0. So I'm left with 4z squared plus 49. So what I see for a pattern, actually I have a little bit of a mistake here. I'm just noticing right here. This is actually minus. Negative 7 times positive 7, negative 49. So a little bit of a mistake there, sorry, but I corrected it. Here's the patterns I notice. My first number is a perfect square. That's just x squared. My last number is a perfect square, 1 squared. Same thing here. This is just 2z squared. and then this last number is just 7 squared. So x squared and 1 squared, 2z squared and 7 squared. Because they are same but opposite, it gets rid of the middle term. So all you have is the square of the first number, the square of the second number, sign in the middle is subtract. So this is the last type of special factoring I want to look at, which is difference of squares. So whenever I have factors that are same but opposite, when I expand those, it just ends up being a squared minus b squared. So I can recognize that if I have two perfect squares that are subtracted, all I have to do to factor them is take the square root of the first one, the square root of the last one, subtract one, add the other. Now, notice this is a difference of squares. There is actually no such thing as a sum of squares, only a difference of squares. So let's look at this one here as our last example. These are both perfect squares because 4g squared is the same as 2g all squared, and 49f squared is the same as 7f squared. So this is going to be a difference of squares. Difference because it's subtracted, squares because they're perfect squares. So I know that this factors into the same but opposite because it gets rid of the middle term. So I'm going to put a 2g here and here, and a 7f here and here. And then I just simply add one and subtract the other. So factoring a difference of squares is the same but opposite factors. We can always check that by applying the distributive properties. So let's look at that. So 2g times 2g is 4g squared. 2g times negative 7f is negative 14fg. 7f times 2g is 14fg, and 7f times negative 7f, negative 49f squared. So you can see my middle terms again are gone. They cancel, and all I'm left with is 4g squared minus 49f squared, which is what I ended up starting with. Okay, so I know that that has factored correctly. So this concludes our factoring of polynomials, our special polynomials, our GCFs, our trinomials where a is 1, trinomials where a is not 1. It is time to say goodbye to our polynomials. Polynomials, yes, these are all polynomials, yes. Goodbye, polynomials. You've served us well. I hope this video helped, and I do look forward to seeing you for the next one.